Alright, so now it is time to discuss how to sketch face portraits when you have complex eigenvalues for 2 by 2 system. Okay, so complex eigenvalue means your eigenvalue will be like alpha plus beta I, right? Now let's discuss. So where do we use alpha when we want to write the general solution of this complex system? Well, we use alpha to write our exponential term in our general solution, right? We always write e to the alpha t. Now think, when time goes to infinity, what happens to the alpha t? It's totally depend on the sign of the alpha, right? So we can have three cases. Remember, when alpha is positive, when alpha is negative, when alpha is 0. What happens when alpha is positive? When alpha is positive, e to the alpha t, when time goes on, it's an exponential growth, right? So you grow exponentially fast. So when time moves on, your arrows in your face portrait will be moving away from the origin, right? Again, the origin is the equilibrium point. Don't forget that, okay? That's something that we set aside in beginning of the chapter 8. So the arrows will move away. So when alpha is positive, it's a unstable 0, 0 is a unstable equilibrium point. Now when alpha is negative, it's an exponential decay. So when time goes on, the arrows will approach to the equilibrium point, right? Will approach to 0. So it is a stable equilibrium point. Now when alpha is equal to 0, that means you do not have exponential term, right? So e to the 0t, right? E to the 0t means it's 1, so you only have trigonometric terms in your general solution, right? You have sine beta t, cosine beta t terms. So what happens then? So I will say that the arrows are neither approach to equilibrium point, so neither moving away. Okay, so it's a semi-stable, but how do I convince you that? But before we going into that, we have to understand the stability of the equilibrium point 0, 0, or the origin is totally decided by who? Alpha, the real part of the complex number, real part of the complex eigenvalue. So alpha is very powerful. All right. Now, how do you draw the solution trajectory? So let me show you something. Because we are not going to use eigenvectors to draw our trajectory. So look at this. So I'm going to draw. So we know, let's take the alpha is equal to 0 case first. Okay. So when alpha is equal to 0, we have e to the 0t. So no exponential term. And let's say our beta is 2. Okay. So it's like 0 plus 2i is the eigenvalue. So sine 2t, cosine 2t. Let's draw one. Let's see what happens. This is like a general solution. So let's take time from 0 to 2 pi, like that's like 6.5. See what you get. The plot is a circle. Okay, so this is alpha is equal to 0 case. Okay, now we have arbitrary constants and we multiply them by vectors, right? Let's choose arbitrary constant 2. So when I put 2 times sine 2t plus like cosine 2t, what happens? You get like a ellipse. Let's 5. Okay. All right. So here's what I want to prove. So let's move on to case 3 first. Let's study this case, how to draw the trajectories. Okay. So when alpha is equal to 0, you don't have an exponential term. And what will be your trajectories look like? Circles or ellipses. Okay, circles or ellipses. That is what your solutions will look like. So how to decide circles or ellipses? Well, we don't do that here in this lesson. Okay, we don't go that far. So it's enough to know it's either circles or ellipses. Okay, all right. So then, okay, when alpha is equal to 0, now you know that it's semi-stable and the shape of the trajectories. We call this a center. The equilibrium point is a center then. Okay, it's a center for an ellipse, ellipse or a circle. Okay, so the equilibrium point, the origin is said to be a center when you have alpha is equal to 0. Now one thing more needed. So we have to show the arrows, right? So we know, for example, in this system, when you see that you have a complex eigenvalue with alpha is equal to 0, let's say it's a circle. Okay, so this is the shape. Now where are the arrows are going? Okay, you can see they are neither moving into the origin or neither going away. They should circle around this circle, right? So is it clockwise or counterclockwise? That's the question. So how do you decide that? Well, pick up a random point. So let's pick up 1 0, the point 1 0. Okay, so now multiply a 0 1 negative 5 0 and multiply by the point vector. Okay, so what do you get? What we get is 0 negative 5. So this point 1 0 is pointed towards 0 negative 5, which is in down. So you're pointed towards down, right? This initial point is pointed towards this point, so it's down. So it's is it clockwise? Yes, it's clockwise. So it's a clockwise orientation. Okay, so you can see it's neither approach or neither goes away. So that is what happens when alpha is equal to 0. Okay, so now let's go on and discuss when alpha is non-zero. So when alpha is non-zero means either alpha is positive or negative. What happens is that you have exponential terms. So let's multiply them by exponential terms. Okay, so multiply this by e to the alpha is positive, e to the 2t. Okay, so times this one is also multiplied, e to the 2t. So what you get is really, let's have a constant, is what you really get is spirals. Okay, here you cannot see it very clearly, but what you get is really spirals. That is what you get. Let's is this one also. So you get spirals. So how? So let me show you. So what you want to do now is when alpha is positive, remember that you get spirals as the shape of the trajectories. So you want to know whether they are clockwise or counterclockwise. Well, for sure you know the alpha is positive means arrows are moving away from the origin. You just need to know it's a clockwise spiral or counterclockwise spiral. So what you do is you pick up a point 1 0 again, like 1 0. Okay, so multiply it by a, so it gives me 2 negative 3. So 2 negative 3 is like here, so it's pointing downwards again. So the spiral will be moving away and clockwise spiral, moving downwards, so clockwise spiral. Okay, so you can see the arrows are moving away and it's a spiral that is moving clockwise. So that is how you draw the solution trajectory when alpha is equal to positive. Important things you need to remember: when alpha is positive, arrows are moving away, then decide the orientation and then you can get the shape of the spiral, right? Okay, decide whether it's clockwise or counterclockwise. Here it's clockwise, and since alpha is positive, this is an unstable equilibrium point. Now when alpha is negative, again you know it's spirals. Okay, so now you pick up a point like 1 0 and you know arrows are moving towards 0 0. So when you multiply a by 1 0, you get negative 2 negative 3. That means negative 2 negative 3 is like here. So this, from this point you're moving this side. So what happens is, so the arrows are, the spiral is this side and it's moving clockwise, but at the same time it should approach. It should approach. The previous picture that I plot was wrong because it did not approach when you draw clockwise arrows. Okay, so here when you draw clockwise arrows, the special thing about this spiral is that it approaches to 0. It's oriented so that it approaches to 0. So you have to keep those two things in mind when you draw the spirals. Okay, if alpha is negative, it should approach, then find out the orientation, clockwise or counterclockwise, then decide the shape of your spiral. Okay, so that is how you draw the face portraits, a rough sketch of a face portrait when you have complex eigenvalues. Okay, all right, thanks.